Hey friends, welcome to the YouTube channel all about electronics. So in the previous videos of the electromagnetic theory, we started learning the concept of the vector calculus from the electromagnetic perspective. And in the previous video, we learned about the line surface and the volume integral. So similarly, in this video, we will learn about the concept of the Dale operator and we will learn about the gradient. So this Dale operator is a vector differential operator and it is represented by this nebula symbol. So in the Cartesian coordinate system, this Dale operator is represented by the following expression. That means here, in this Cartesian coordinate system if you see, then each component of the Dale operator represents the partial differentiation in the respective direction. But here, the representation of this Dale operator changes with the coordinate system. For example, in the Cartesian coordinate system, this is how the Dale operator can be represented. And similarly, this is the representation of the Dale operator in the spherical coordinate system. So by looking at these expressions, you must be thinking that why the representation of the Dale operator is different in the cylindrical and the spherical coordinate system, right? So the reason is that in the Cartesian coordinate system, each coordinate x, y and z represents the distance. So therefore, the small change in the each direction can be simply represented by the dx, dy and the dz. But on the other hand, in the cylindrical coordinate system if you see, then this phi represents the angle. So therefore, the small displacement in the phi direction cannot simply represented by the d phi, and rather the displacement in the phi direction is represented by the arc. So in this case, that is equal to rho times d phi. And in fact, in the previous video, we have already seen that in the detail. So for more information, you can check that video. So therefore, in the cylindrical coordinate system, instead of simply d phi, we have this rho times d phi. Likewise, in the spherical coordinate system if you see, then here both theta and phi represents the angle. So therefore, the small change in the theta direction is represented by this r times d theta. And likewise, the small change in the phi direction is represented by this r times sine theta times d phi. And as I said in the previous video, we have already seen these things in the detail. And overall, this is how the Dale operator can be represented in the different coordinate systems. So now, this Dale operator can be applied to both scalar as well as the vector fields. So whenever it is applied to the scalar fields, then it can be applied in the two ways. So in a one way, we will get the gradient. And in the second form, we will get the Laplacian. That is the second derivative of the scalar field. And similarly, in a two ways, this Dale operator can be also applied to the vector field. So whenever we perform the dot product of this Dale operator and the vector field, then it defines the divergence. And likewise, the cross product of this Dale operator and the vector field defines the curl. So one by one, we will understand each of them and we will understand the physical significance of the each term. But in this video, first let us see the gradient. So when we operate the Dale operator on the scalar field, then we will get the gradient. And this gradient is the vector quantity. That means it has both magnitude as well as the direction. So now, let us see the physical significance of this gradient. So at any given point, the gradient of the scalar field defines the maximum rate at which the scalar field is changing. And it also shows in the which direction it is changing. That means at any given point, the gradient points in the direction where the rate of change in the scalar field is maximum. And its magnitude defines the rate of change in the scalar field at the given point. So for example, we know that the temperature is the example of the scalar field. And let's say this is how the temperature is changing in the 3D space. So here, the blue represents the colder temperature, while the red represents the hotter temperature. So at any given point, if we move in any direction, then there will be a change in the temperature. But at any given point, this gradient shows the direction where the maximum change in the temperature can occur. That means here, all these arrows shows the maximum direction of the change in the temperature at the given point. So now, let us see the mathematical representation of this gradient. So let's say, if V is the scalar field in the Cartesian coordinate system, then the gradient of the V can be defined as this del V divided by del X times Ax, plus del v divided by del y times ay. And similarly, the third term will be equal to del v divided by del z times az. Similarly, if the v is defined in the cylindrical coordinate system, then this is how the gradient of v can be defined. And likewise, this is the representation of the gradient in the spherical coordinate system. So earlier, we have seen that how to represent the del operator in the different coordinate systems. And from that, we can easily write the expressions of the gradient in the different coordinate systems. So now mathematically, let us also prove that indeed this gradient points in the direction where there is a maximum rate of change in the scalar field. And we will prove that by taking the scalar field in the Cartesian coordinate system. So in the previous video, we have seen that the differential length dl in the Cartesian coordinate system can be defined as this dx times ax plus dy times ay plus dz times az. Now here, if the v is some scalar field, then the change in the scalar field dv can be given by the following expression, right? That is the del v divided by del x times dx plus del v divided by del y times dy. And the third term will be equal to this del v divided by del z times dz. And the same expression can also be represented like this. That is the dot product of this term and the dl. Because here, if we perform the dot product, then we will get the same expression. So let's say this term is equal to g. So therefore, this change in the scalar field can be written as this g dot dl, right? Where this g can be represented by the following expression. So now, as per the definition of the dot product, this g dot dl can be also represented as this magnitude of g times magnitude of dl times cos theta. Or we can say that this dv divided by dl is equal to this g times cos theta, where the g is the magnitude of the following expression. So here, this dv divided by dl will be maximum whenever this cos theta is equal to 1. Or we can say that whenever this theta is equal to 0 degree. So it will happen when the g and the dl both are pointing in the same direction. And at that time, the change in the value of the scalar field will be maximum. And at that time, this dv will be maximum. So we can say that whenever this dl is pointing in the direction of the g, at that time, the change in the scalar field will be maximum. And we know that this g is nothing but the gradient of the v. So therefore, we can say that the gradient of the scalar field always points in the direction where there is a maximum change in the scalar field. So similarly, these are the expressions of the gradient of the scalar field in the different coordinate systems. So now, if you see the properties of the gradient, then it is very similar to the properties of the differentiation. So whenever it is required, we will use these properties. So now, let us take one example so that the concept of the gradient will get clear to you. So here, let us find the gradient of the scalar field, which is given by the following expression. So here, as you can see, the scalar field is given in the spherical coordinate system. So therefore, the gradient of the scalar field can be given by the following expression. So here, first let us find the first term. So here, this del w divided by del r can be given as these 10 times this sine square theta times cos 5 times del divided by del r times r. And we know that the differentiation of the r is equal to 1. So therefore, this term is equal to 10 times this sine square theta times cos 5. So this will be our first term. So similarly, let us find the second term. So the second term can be given as 1 by r times this del w divided by del theta. So for that, here this 10 times these r cos phi are constant. So therefore, this term can be written as this del divided by del theta times this sine square theta. So now we know that this sine square theta can also be written as 1 minus cos 2 theta divided by 2. So for this specific term, we will have this 1 by 2 times del divided by del theta times this 1 minus cos 2 theta. So here Since the 1 is constant, so its differentiation will be 0. And we know that the differentiation of the cos 2 theta is equal to minus 2 times sin 2 theta. So therefore, we can write it as 1 by 2 times this 2 times sin 2 theta. So here, this 2 will get cancelled out and the differentiation of this term is equal to sin 2 theta. So therefore, we can say that this term is equal to this 10 times sin 2 theta times cos 5. So this will be our second term. So likewise, let us also find the third term. So here, the third term can be given as this 1 divided by r sin theta times this del w divided by del 5. So that is equal to 1 divided by this r sin theta times del w divided by del 5. So here, for this partial differentiation, this 10 times this r sin square theta is constant. So therefore, let us take it out and further we can write it as this del divided by del 5 times this cos of 5. So here this r will get cancelled out and we will have this 10 times sin theta, and we know that the differentiation of the cos 5 is equal to minus sin 5. So therefore this third term will be equal to minus 10 times sin theta times sin 5. That means this will be our third component. So if we combine all the three components, then the gradient of the scalar field can be given like this. So in this way, we can find the gradient of the any given scalar field. So later on, we will see that how this gradient will be helpful in understanding the different concepts of the electromagnetics. But I hope in this video, you understood what is gradient and you also understood the physical significance of the gradient. So similarly, in the next video, we will learn about the divergence. So if you have any question or suggestion, then do let me know here in the comment section below. If you like this video, hit the like button and subscribe the channel for more such videos.